So this is Chapter 2 homework. The conceptual questions are ones we'll go over in class. You've got pictures of those. So this is the book homework. Problems 7, 10, 20, 27, 39, 49, and 57 out of Chapter 2. So number 7 and number 10, we're looking at aspects of blood flowing through, I think it was an aorta, the ascending aorta. And it gave a graph something like this. So in order to figure out how far it goes, you would take the integral or the area of the velocity time graph. So there's a couple ways you could do that. You could divide it into a couple triangles or one triangle, but essentially we've got a 0.2 second interval, and that is multiplied by 1/2 times the maximum velocity. And that gets me 0.08 meters in that time. For number 10, it's asking about the acceleration of the blood. Well, during this first phase here, the slope of the graph is 16 meters per second squared. In the second part of the graph, we've got 3 times as long for the same change in speed, but it's a negative change in velocity, and so it's negative 5.3 meters per second squared. Number 20 is an interesting problem, and I'll put that up there along with 27. Well, I think number 20 is basically saying you've got a ball that's thrown up at 20 meters per second, not thrown up, but you know what I mean. Goes up, comes back down, and lands in a hole or a pit that is below the initial starting point. And that is 10 meters below. So I didn't draw that particularly well. And it's asking a couple questions. One is, what's the rock's velocity as it hits the bottom of the hole? There's a couple ways you could simplify this. One is, knowing the symmetry of this problem, when the rock falls back to this ground level height, it'll be going 20 meters per second again. So gravity acts against it on the way up, with it on the way down. So therefore, you could use this 20 meters per second as an initial velocity, this delta x as 10 meters, and acceleration is 9.8 or 10 meters per second squared. And you could use that and find out the final speed. And the velocity is 24.4 meters per second down. To find the time, there's a couple ways you could do that also. There's a number of ways. The easiest, I think, is looking at dv dt, or change in velocity over change in time. So the final velocity is 24.4 down, the initial velocity is 20 up. So we need to pick our direction as positive. I chose that as down. So 24.4 minus negative 20 over 9.8. Because really the speed has changed by 4.4, the velocity has changed by 44.4 meters per second. So that's going to take 4.53 seconds. For number 27, we've got a rocket, and actually no, we don't. We've got 3 graphs. They all start at 10, go to 30, end up at negative 30 after 8 seconds. For particle A, it's a position time graph, particle B, a velocity time graph, particle C, an acceleration time graph. So it's pretty cool. You're told the initial conditions are at 0 seconds. You're initially at 10 meters per second, which definitely agrees with B. It agrees with the slope of graph A. And for graph C, it doesn't matter. We don't have that information about initial velocity. But it was given. So looking for particle A to find the velocity at 7 seconds, we need to look at the slope of this graph. So the slope of a position time graph gives us a velocity that's negative 10 meters per second. For B, finding the velocity at 7 seconds, this is a velocity time graph. We just look at the y-axis value at 7 seconds. That's negative 20 meters per second. For C, it's a little bit more complicated. So essentially what we need to do is we need to look at the area of this graph. So I'm not sure if I can scribble this in or not. We'll see. Maybe I can. So we're looking at the area in here. It's a positive area. And we'll be subtracting off the area down. Oh God, that's awful. The area down there is a negative area. So up to 7 seconds. And you can use symmetry to do that a little more simply. I think what you get then is you get a positive of 75 meters per second as the area. You started at positive 10 meters per second, or pardon me, positive 65 is the area. I counted that by 6.5 boxes in the graph. and you started at 10 meters per second, so that ends up at a velocity of 75 meters per second. 39, you were given a set of 3 kinematics graphs, and it's a ball rolling on a track, and you're asked to draw the track. So initially here, for me, the velocity graph is the easiest to look at. These shapes are hard to know whether it's curving or straight. This is not so hard. So I've got a positive acceleration here, 0 acceleration, a steeper or greater magnitude of positive acceleration here, and then no acceleration. We're always moving to the left because we always have a negative velocity. So we've got a ball going up a ramp at an angle, and then it reaches a level surface, then it goes up a steeper angle, then it reaches a level surface. So positive acceleration, more positive acceleration, and those agree with those graphs. Somebody's texting me. Okay, number 49. What we've got with that, I think that's the rocket one. Yeah, that's cool. 200 kilogram weather rocket, 100 kilograms of fuel. That does not matter. And it's accelerating at 30 meters per second squared upwards for 30 seconds. And so you're asked to find the rocket's maximum altitude. Well, you really need to think about this in 2 parts. One is, how far does it go up during the 30 seconds? That's using this, I guess it should be delta y really equals 1/2 at squared. That comes out to 13,500 meters. But then you've got to realize it's moving fast upwards at the end of the fuel burn. And although gravity will accelerate it downward, it's going to continue upward for quite a bit of time. So I found the velocity at the end of the 30-second burn by using a times t, 900 meters per second upward. If the distance at this point, I can look and say that the final velocity at the tippy top of its path is 0. The velocity right after the fuel is gone is 900 meters per second. And the acceleration is down at negative 9.8 meters per second squared. I get 41,330 meters there. So my maximum altitude is 54,800. The cool thing about that is notice there's far more distance covered after the fuel is gone than when the fuel is being burned. That's true of a lot of the rockets launched into orbit as well. So, they only need a few minutes of fuel in order to get them up fast enough to carry them into a stable orbit. The second part of this is looking at the time that it takes for the object to fall back down to the ground. So now there's 3 intervals. The time up when the rocket's on, I call that T1, time up when the engine is off, T2, and time when it's falling back down to Earth, T3. T1's easy, it's 30 seconds. T2 I'm solving for here, using VF equals VI plus A times T. And here, if I know my maximum height, which I figured out, I can figure out the time it takes to fall. All 3 of those equal about 228 seconds. The final thing is drawing a velocity time graph for this. So the key thing with this is during the first 30 seconds, you've got a slope of positive 30 meters per second squared. During the last amount of time, which would be the last 198 seconds, you've got a slope of around negative 10, negative 9.8 meters per second squared. And so it's going to end up with a velocity downward of about a negative 1,040 meters per second right before it hits. The last one, 57, I solved 2 different ways. We'll probably go over this in class. But the key thing here, if you can use multiple ways a lot of times in physics to solve things, kinematics is probably what you're thinking of because this was the chapter with kinematics. Energy is another way. So when I look at this, I draw this angle. I know that G would accelerate it downward. Mg would be the force downward. G cos theta would be the normal component. G sine theta would be the parallel component. Well, in fact, since there is a normal force from the hill up and to the right, that cancels out the normal component of gravity. So really the net force would be mg sine theta. And since we use the master formula of A equals F net over m tot, then if this is going to be mg sine theta over m, that's how the acceleration becomes g sine theta. So in this case, I'm going to use this formula for kinematics to figure out the final speed. I'm trying to find that. I have 0 initial speed. That's easy. 2, that's easy. acceleration I just found is g sine theta. Not too bad. X. Well, here I labeled it as L, so I kind of screwed up with that. Okay, how do I find out that distance? Well, if it's sliding down from a height h and an angle theta, then overall this distance is going to be L equals h sine theta. Wait a second. L sine theta equals h. Sorry about that. So L times sine theta equals h. And so therefore, to get L, it's h over sine theta. Sine theta on top, sine theta on bottom. So we get that Vf squared equals 2gh. Vf equals radical 2gh. Using energy. Potential energy at the top, here, would equal kinetic energy at the bottom. mgh, 1/2 mv squared. Vf equals radical 2gh. That seems a lot simpler. Sometimes energy is a lot simpler and we just don't think about it. So notice it's the same formula because it's not different physics just because you think about it with energy or because you think about it with kinematics. So down here the angle doesn't matter. If you release the height at 30 centimeters or 0.3 meters, your final speed will be 2.4 meters per second. So hopefully that's okay. I don't know if anyone listens to this. If you're the first one to listen to this, behold, the magic word is donut. Tell me the magic word, and you will get a donut. Thanks. Time to sign off. Radio Free America.